Our next speaker here in this room is going to be Douglas Crockford, who is known for having made the first significant discovery of the 21st century, which was that JavaScript actually has good parts. Also for discovering the JSON format, widely known and widely loved. Ladies and gentlemen, let's welcome Douglas Crockford.
Good morning. I'd like to talk to you now about numbers, because I assume we're all programmers here. Everybody programs computers. Anybody? Any programmers? Yeah. And the only thing computers know how to do is manipulate numbers. That is literally all that they can do. But somehow we figured out a way to map just about everything onto numbers so that computers now mediate almost everything that humans do in the world, which is magical. So because numbers are so fundamentally important to what we do, I thought we'd spend an hour talking about numbers. So numbers start with fingers. The first place I think where humans experienced numbers were counting small numbers of things on our fingers. But fingers are much older than numbers. So the original application use case for fingers was holding onto tree branches and picking and eating fruit. And we were really happy doing that for a long time until the climate changed and things got drier in Africa. We had to drop out of the trees and walk around looking for other sources of food. It turned out that fingers were also very good for manipulating tools. For example, a stick that you could use to dig in the ground and pull up a tuber, and then a rock to smash the tuber until it was soft enough to eat with our cute little monkey teeth. And as we did things like that, we would level up. And in the upgrades, we were able to turn volcanic glass into knives and to manage fire, which increased our range of food because we could now cook things which would allow us to eat things that we couldn't adjust otherwise. And that allowed us to level up again. Eventually we get to agriculture, and so we don't have to move around anymore. And by settling down, we start growing into larger communities. And so tribes and clans become villages and cities and countries. And as we scale up, our abilities with numbers become much more important because we need to keep track of how many of us are there, how much food do we have, how do we plan for the winter, and so on. And that leads to the invention of accounting. Accounting was critically important as we scale up to manage ourselves and to make sure everybody gets fed, everybody gets taken care of. And accounting first happens as notches on sticks and marks on walls and knots in strings. But eventually, you've got so many numbers that you need some way of keeping track of what is it that this number represents. And so we invent writing. And writing is the most important thing I think we will ever discover. Everything that comes after is a result of writing or a byproduct because it's a way of preserving information, of communicating information, of creating information. I don't think we'll ever do anything again as important as writing. Writing, amazingly, was invented in 3 different places at 3 different times. As far as we can tell, there was no interaction between these places, so they were 3 independent inventions. The first was in the Fertile Crescent. The smart money thinks it happened in what is now Iraq. I think it happened in Egypt. It happened again in China, and then it happened in America in the pre-Columbian civilizations. They had a very sophisticated writing system. Unfortunately, it didn't survive the Spanish invasion, so that's enough of that. So let's look at some of the number systems that were used in antiquity. So we'll start with Egypt. Egypt had an additive number system. So there were a number of symbols which each represented a power of 10, and you would repeat the symbol for as many of those units as you needed. So a 1 was a stick, a 10 was a coil of rope, 10,000 was a finger, a million was a guy saying, "It's a lot." It's just. But the interesting thing is, this guy doesn't mean a lot, he means exactly a million, which indicates some real mathematical sophistication. You don't have a symbol for exactly a million unless that would be useful somehow. The Egyptian writing system, being one of the early writing systems, was very, very complex. And they taught it to the people that they traded with, including the Phoenicians. The Phoenicians were brilliant traders and sailors. They operated all over the Mediterranean and the Western Atlantic. No, Eastern Atlantic. Yeah. And they greatly simplified the Egyptian system. So the Egyptian system had thousands of characters in it. The Phoenicians knocked it down to a couple of dozen. So they used Egyptian symbols simplified to represent specific sounds. And it was a very workable system, and they taught it to the people that they traded with. And many of those cultures adopted the Phoenician system. And basically that's what we're still using. They taught it to the Greeks, who changed their writing system to the Phoenician system. And at that time, the Greek alphabet had 27 characters in it. And so they came up with this system for dealing with numbers. So they have 1 through 9, 10 through 90, and 1 through 100. Again, it's an additive system, but it can be much more compact than the Egyptian system, because we've got all of these extra units in there. And if you need to get bigger numbers than these, you could put an accent on something which would multiply it by 1,000. The Greeks taught their language system to the Romans, who adopted and modified the alphabet to fit their own language. But their number system more closely resembles the Egyptian system. They took the Greek idea that we'll use letters to represent the digits, but the way they composed it works more like they did in Egypt. So they replaced the stick for the 1 with an I. The 10, which represents a bundle of sticks tied together, is represented as an X, and the coil of rope becomes a C. And then to make it more compact, they came up with the idea of having half things. So you take an X and cut it in half, that's a V. You take the C and cut it in half, that's an L. And then to make it even more compact, they made it subtractive as well as additive. So if you have a digit in front of another digit which is smaller than the next one, it subtracts instead of adds. And it worked. You know, they were a great civilization. They occupied a big chunk of the world for a long time, but I can't imagine doing multiplication in this system. It just seems really hard. Meanwhile, in China, completely independently, they developed their own system. And, you know, coincidentally, their system for 1 is also a stick. So, you know, there are similarities like that. And it's a very elegant system. They've got modifiers for 10, 100,000, and then further modifiers to get higher. So the way they wrote numbers in symbols is very similar to the way we speak numbers when we're saying them out loud. That we don't tend to say a number of digits. We'll insert words like 100 or 1,000 into the words, and they did something very similar in their symbols. Meanwhile, in India, they come up with a really interesting system where they reduce the number of characters that they need to deal with down to 10. They've got the 1 through 9 that we saw in other systems, but they also add a 0. And now it's a positional system. And they're able to do some very interesting things using that system. They teach it to the Persians, who call them Hindu numbers. The Persians teach it to the Arabs, and the Arabs teach it to the Europeans, who call it the Arabic system. So this is the same number represented in each of these systems, and all of the systems work. I don't think it's inevitable that you get from one to another, that any one of these would work. And when you think in terms of computerization, computers could work as well in any of these. So the computers don't care. They all worked for humans. They all worked for us. So, you know, there's a tendency when we look at the history of technologies to say that inevitably we'll get to this thing. And I don't think it was inevitable. But there were some good things that came out of the Indian system. So being positional, we could think of it as we put numbers on the number line, and each position on the number line represents a factor of 10. And so the written expression of a number is actually a shorthand for a polynomial. And so this is where our idea of polynomials come from. This is a really important mathematical concept. It sort of falls out of the number system. then the Indian system can also deal with negative numbers, which is something that nobody else had. They had the idea of taking things away. I will take away 2 loaves of bread, but they didn't have a notation or a way of thinking about negative loaves of bread. That didn't make sense. That wasn't something you could count. But the Indian system allowed you to represent these things which were meaningless in the real world, but are actually really important in accounting. And once you recognize that you have negative numbers, then the number line goes infinitely in either direction. So now you have a way of dealing with fractions. All of the other systems had fractions, but they did them in a very different way. For example, Egypt had this remarkable system where they had the sum of reciprocals. So they had a number system based on 1/2 and 1/3 and 1/4 and 1/5 and so on. They had a complete set of these little things, and they would add them together to try to make a whole fractional bit. And they had these complicated tables which you used for adding and subtraction. I'm guessing that they figured the system out by using weights. They had put lots of little things on and worked it out, but it was complicated. But in the Indian system, it's really straightforward. You use the same rules for dealing with fractions as you do with integers. You just have to keep track of where the decimal point is. So in the original Indian notation, they would put a line above the units column, because you needed to know, where is the power of 0. And when it moved to Europe, that changed from an overline to a mark behind the units position. And when we start doing typesetting, then that mark gets formalized either into a period or a comma. And in some countries it's a period, in some it's a comma, and it seems to be pretty random which one it's going to be. And it's not a problem because each country was kind of on its own. But now we're on the internet, and now you can display a number anywhere in the world. And so you've got things like this. Is this 2 or is this 2,000? It's off by a lot. You could average it. You say, well, let's say it's about 1,000. That's that's very far from right. So ultimately, I think the world is going to want to settle on a universal standard, that there should be one meaning for this, so that we don't have confusion as we cross our borders and go into cyberspace. So I think eventually we will decide that we're going to go with the period. And I think the reason we're going to go with the period is going to be because of you. That the reason we're going to have international numbers is because all of these numbers are flowing through your software into the internet. And your programming languages really want to be using the period. And so eventually you're going to convince the whole world that they want to be using the period too. So it's interesting that all of these systems were using base 10. Some of them influenced each other, but the Chinese had no interaction with Egypt, so there was no way they could have known that. So how did they both get base 10? Is that an amazing coincidence? Or maybe they counted their fingers and yeah. So that works. Base 10 is a fine system. There were other cultures that used 20. For example, the American societies, the Mayans and all those guys, they were using 20. So how did they get 20? I'm guessing they added all of their fingers and they added all of their toes. There are some societies that use 12. And we can still see that today, right? Our timekeeping is in 12. We have 12 hours in a half day. In my stupid country, we still have 12 inches in a foot. There was 12. So how did people get to 12? I'm guessing it was the 10 fingers in each foot. So you could count that way.
12 bones in your fingers except for thumbs. So 1, 2, 3.
Yeah, I'm not buying that. So there's some cultures that were using 60. For example, in Sumer in Mesopotamia, they were counting to 60. So you go, how do you count? What are they counting? What I think happened was, as the villages grow into cities and the cities into city-states, they start annexing other groups, right? So you're now part of us now, and you'll convince them either by sharing technology or by smiting them And eventually they get tired of being smited, and then they decide, okay, we're with you. And so there were groups that were doing their accounting in 10 and groups that were doing accounting in 12. And the new king said, we are now unifying. We're going to all have common books because it's too complicated if you're counting in 12s and you're counting in 10s. So figure it out. Get onto one number system. Pick the one that's best, and that's how we'll go forward. And so they put together a standards committee, and that standards committee is tasked with, is it going to be 10 or 12? And the standards committee can't decide. So the standards committee can't do what they usually do, which is we'll go with both. Instead, they decide we'll go with a mutually disagreeable compromise, the thing that doesn't work for anybody. We'll go with the least common multiple of the two. And so that's how they got to 60. Which was, and it worked. They had it was a very successful nation state, and they did a lot of stuff. And it turned out, coincidentally, there were a lot of benefits to being in base 60, because there are lots of forms of division which divide evenly into 60 that don't in the other systems, because it has this factor of 3 in it. So it worked. They weren't disadvantaged necessarily from that, although to my idea it was a very complicated number system. But it still exists, right? Because we still keep time with this. We have 60 minutes in an hour. And if you've ever had to do time calculations, it's really annoying that we're still doing that stuff. Or if you've done geographic computation, we're still using minutes and seconds. A standards committee made a bad call 5,000 years ago, and we're still stuck with it, which kind of shows the consequences of bad standards. That a standards committee will make a decision for something which was expedient at the time but has no long-term value, but the consequences of that decision can last millennia, literally. So one of the really important discoveries was the binary system, that the basis didn't have to be 10 or 60 or 12, that it could be 2. And the benefit of that is that computerization really loves that. There were early attempts to try to build decimal computers, but binary was just so much easier to do, and the circuits could go much faster and be much more reliable, and we're still doing binary. So when you're doing binary, you have to figure out how are we going to deal with negative numbers. So you're going to have a sign bit of some type, and there are 3 basic ways of dealing with a sign bit. The first is called signed magnitude, where you'll designate an additional bit, and that bit will either be at one end or the other, and it'll either contain 0 for positive or 1 for positive. It doesn't matter, you just need to be consistent. The problem with signed magnitude is that there are now 2 versions of 0, 0 and negative 0, which doesn't make sense mathematically, so it's sort of a hazard. You need to be aware of it. Another way to do it is ones complement, where you also have a sign bit, but the interpretation is to make a negative number, every bit gets flipped. We complement it. And that works. It's very effective. There are many computers that work that way. But when you're doing addition, you have to deal with end-around carry, which means if you do an add and if a bit falls off the end, you have to take that bit and add it back to the other end and let it ripple through again. Then there's two's complement, which does the end-around carry at the time that you do the negation, so that on adding, if something overflows, you just throw the bit away. And one advantage of that is there's no negative 0 anymore. So that's a good thing. The bad thing is that there is now a negative value that has no corresponding positive value. So if you try to take the absolute value of that thing, you still get a negative number, which is bizarre. So I think that shouldn't happen. What we should have done in all of these cases, we should have used either that extra negative value or the minus 0 to represent null or some sentinel that this is not a valid number. For example, in Java, we see a method called indexOf. And if we call indexOf looking for a substring in a string, it needs to communicate failure. If the failure isn't an exception, you don't want to throw an exception on this because it's a It's not an exception. It's a likely consequence that we won't find the thing. But Java's type system didn't allow them to return null or some other thing which indicates the thing that you're looking for was not found. So instead there's a convention that they returned -1 because that's all their crappy type system would allow them to communicate. And that's a problem because if you were to just take this value and insert it into a further computation, which assumed that the thing worked, then -1 is not a meaningful position and you're going to create an error. And JavaScript copied this even though it didn't have to. JavaScript has a much better type system than Java, so it could have communicated nan or null or undefined or some value to indicate that the search failed. But it just copied Java, unfortunately. So let's talk some more about types. What should the result type be of adding two 32-bit integers? Any guesses? Correct. The answer is int 33, because you can have a carry, which will then make the word 1 bigger. Java, unfortunately, gets this wrong. So that's a problem. So let's look at another one. Let's say we multiply two 32-bit integers. What's the type of that? Close. It's 63, but you're very close. You did much better than Java. Java said it was 32, which is wildly off. So it turns out integer multiplication in Java is really dangerous because the likelihood that you're going to cause an overflow, which is what happens here if you have more bits than will fit, an overflow is a really bad thing. So let's look ideally, what should happen if an overflow occurs? There's one school that says that's when we store the null value. And that would actually be a reasonable thing. So we would say that extraneous minus number, instead we'll use that as the sentinel for when something overflowed. That actually would be a really useful thing. Or we could store the largest thing that actually does fit. This is called saturation. This is reasonable to do in computer graphics and signal processing, but you don't want to do it in financial applications, right? Or you could fault. The machine could have an exception or something could go on, so some higher level software could decide, well, this thing's obviously not going to work and go off and do something else. But if what you really want to do is to maximize the creation of error, then what you want to do is discard the most significant bits without notification. And that's what Java does. So there's all this talk about how types are helping you be protected from errors. The type system is the cause of the errors. So let's look at scaled arithmetic. This is what happened on the first computers in the 40s. These machines were designed and built by mathematicians who wanted to work with the real numbers, but they only could afford integers. So they did scaled arithmetic. And scaled arithmetic is complicated to write. You can only add if two numbers have the same scale factor. If they have different scale factors, you have to make them conform. That's complicated. Multiplication requires that you also divide out the scale factor. And division requires that you first multiply in the scale factor. It's just complicated stuff. So some genius got the idea that and finding the ideal scale factor is hard because you want to find something that preserves as much precision as possible without overflowing. And knowing your data well enough to know what that number is hard. So someone figured out we should have floating point, which can better approximate reals than scaled arithmetic can. And it's much more convenient, much easier to write. Unfortunately, they were really slow. So the first floating point standard looked something like this. There'd be a significand, which was just the base number, the thing that contained all of your digits. Then there'd be a second number, which would be the scale factor, and that would determine where the decimal point was. It was pretty straightforward, but they were slow. So when they decided to start moving the stuff into hardware, the basis changes into binary, because binary computers are much better at doing binary than doing decimal. In particular, doing it this way, you don't need to have a division by 10, which is difficult to do with vacuum tubes. So the value of a binary floating point number is the sign times the significand raised, or times 2 raised to the exponent. Except it's more complicated than that because the exponent is biased, and the reason it's biased is to allow for an integer comparison to do relative comparisons on floating point numbers. If everything's normalized, you can much more quickly determine if one thing is bigger than another, which in the 50s was a brilliant optimization. Today, Moore's law gives us other ways to do it, so not so much. The exponent also hides a subnormal mode, which allows you to have very small numbers and zeros. But the problem with binary floating point is this. 0.1 plus 0.2 is 0.3 with a little bit extra, and it's actually worse than this. This extension actually goes on quite a long way. And as a result of this, binary floating point really isn't suitable for dealing with most of the numbers that humanity is interested in, particularly the ones that represent their money. So why did this happen? Well, if we look at the binary expansion or binary representation of this, we start to approach 0.1 by adding 1/16th and 1/32nd, and that gets us pretty close, but clearly we're not close enough, so we're going to need more bits. So when you fill it out and you look at all the bits, you see that 10th in the binary system is a repeating figure, similar to the way that 1/3 is a repeating figure in the decimal system. So you can have this pattern of 0, 0, 1, 1 going for infinity. So if you have infinite storage, you will get exactly 0.1. But we don't, because our computers are finite. So it's always going to be approximate. So we can't have the infinite expansion, so we're going to have to cut it off someplace. If we cut it off before a 0, then we're going to lose all of the remaining ones, which means our number is going to be too small. And if we cut it off before a 1, then we're going to round up, and our number is going to be a little too big, that we cannot ever get exactly the number that we want in this representation, which is a problem because the associative law only holds if all of the inputs, outputs, and immediately results can be represented exactly. And since we can't represent the decimal fractions exactly, it means that most of the numbers that we might want to calculate with cannot be represented perfectly, which means the order in which you add things can change the result of the computation, which is really scary. So that's why business couldn't use binary floating point. Instead, they used binary coded decimal, which represented a digit as 4 bits. So it's less compact, but it was much easier to deal with. And binary coded decimal would look like this. And there were 6 codes left over, which could represent things like signs and decimal points and ends of fields and stuff like that. So one of the difficult things about binary floating point is it's difficult to convert it to decimal text. That conversion needs to be correct, optimal, and unsurprising. And that turns out to be really hard to do. All of our programming systems are basically trying to hide a lie from us, that the representation that they're interfacing with cannot represent the stuff that we think it's representing, but we don't want to see what it actually thinks the numbers are. And so it's trying to find compromises, things which are approximately what they think we might want, but often it's not quite there. It's also computationally expensive. So if you look at JSON processing, what's the most expensive thing about JSON processing? It's the numbers, by far, just because the numbers are really inefficient. I've seen people wanting to go to binary formats because they think it's going to be faster. Generally, it's not faster, but the part of it that might be faster would be the conversion of numbers. But it won't be portable. So in most modern programming languages, there's a confusion of faulty types. So whenever you're making something, you have to decide which one of these is it going to be. And if you get it wrong, it can literally be disastrous. So an example of a disaster caused by the selection of these things is the Ariane 5 failure. Anybody remember that one? So the European Space Agency built this beautiful rocket ship, and it takes off, and seconds later it has to self-destruct. And it's estimated that the cost of that failure was $500 million. You probably haven't had any bugs yet that are worth $500 million, but you know, it could happen. So that rocket controller code was written in Ada, and I've translated it into Java because the same bug is possible in Java. That there was a value called horizontal bias, which was a double, and they converted it into a short, and it overflowed, and that got fed into the controller, and the controller got confused, and the rocket went out of control. So anytime you cast a number, there is a potential of a $500 million failure. So JavaScript, on the other hand, only had one number type, and having one number type would avoid large classes of errors. Had the Arian 5 controller been written in JavaScript, it might have gotten into orbit. Unfortunately for JavaScript, it's the wrong type because it cannot represent the binary or the decimal fractions. And the decimal fractions are really interesting to humans. It's how we think about numbers. And having a number system in our computers that thinks about numbers differently than we do is a problem. I mean, we're in the 21st century and we cannot add 0.1 and 0.2 together. We should be able to do that by now. So I'm recommending another type instead to replace the binary floating point that we have now. I call it DEX64. I recommend that DEX64 be the only number type in well-designed application languages going forward. It's not suitable for some applications. For example, in chemistry and physics, occasionally they'll deal with really big stuff. This is more for the stuff that all of us are doing every day, and I think it'll do what we need to do every day really well. If there's only one number type in your language, you cannot make an error by choosing the wrong type. And in hardware implementations, DEX64 integers can be added in a single cycle, which eliminates the performance justification for ints. The numbers work the way humans think numbers work. So the techniques that you were taught in school for adding and multiplying and dividing numbers on paper, you'll get the same results with DEX64, just much faster and much more accurate. But you don't get the surprising things like the random 4 at the end of 0.1 plus 0.2. And by eliminating that confusion, we'll eliminate errors. And conversion of DEX64 numbers to text and back is simple, efficient, correct, and unsurprising. And DEX64 can accurately represent decimal fractions to 16 digits, which I think should be big enough for anything that you'll ever need to do. So this is the representation. We have a 56-bit coefficient and an 8-bit exponent. The exponent is at the end because on Intel architecture, you can decode that for free. It costs no instructions to get at that byte, and so it's very efficient in a software implementation. And the value of the number is simply the number is the coefficient times 10 to the exponent. That is literally the thing. There are no other encoding tricks, except that there is one exponent that is reserved, which will represent everything which is not a number. So that we can use that to represent, well, null and true and false, and possibly every object. So we could store an object reference in the top part of the coefficient, so we just have one 64-bit thing that we pass around that represents everything. And there's a software implementation on GitHub, so if you're a language designer and you want to practice with it, it's there. And eventually, I hope we'll also have implementations for ARM and maybe for other processors. So let's talk about 0. Let's have some fun with 0. So what is 0 divided by 0? Any guesses? Anybody? So most mathematicians would testify that it is undefined. And by undefined, they don't mean the silly thing that JavaScript means by undefined. They mean this isn't something you can even think about, that you cannot reason about 0 divided by 0. Don't talk about it. Just don't, because it doesn't exist. It's meaningless. Don't. Okay. Another theory is that a well-written program will never divide 0 by 0, so it doesn't matter what the machine does. So if it catches fire, that would be all right, because it can't happen. Except we know that it will happen, right? If there's something that a program is allowed to do, it'll happen. So we probably don't want the machine to catch fire. You might want to substitute some null or nan or some other value which says, you tried to do something and it didn't work, so here's something to represent the thing that didn't work. And that's a reasonable thing. Another potential answer is 0. And this actually makes sense in business applications. For example, we sold 0 units last month. Our total profit on those units was 0. What was the average profit per item? You can't say, boss, you can't. The answer is 0. That's the reasonable thing. There are some mathematicians who'd say, well, n over n is 1. That there are some problems where that actually makes sense. I haven't seen one, but I've heard it's true. I once worked on a mainframe where the answer was 2. If you had 2 floating point zeros and you divide them, you would get exactly 2. And that was a machine designed by Seymour Cray, the greatest computer designer in history. And I can imagine a conversation that happened at Control Data Corporation, where someone said, hey, Seymour, there's a problem with the divide instruction. So what's that? When you divide 0 by 0, you get 2. So, well, people shouldn't be doing that. Well, yeah, of course they shouldn't be doing that, but it happened, so maybe we should do something about it. He said, well, look, divide is the slowest, most complicated, most expensive operation on the machine. And if I put in a 0 divided by 0 check, it's going to make the machine even more expensive. It's going to add one more cycle to the thing that's already the slowest thing we do, which is going to slow down every correctly written program just so that some idiot can write 0 divided by 0 and get who knows what it should be anyway. So, no, I'm not going to do it. So he didn't fix it. And as far as I know, I'm the only person who ever tried it. So why do I care about that? Well, I don't care about that so much. I more care about this case. What is 0 times n? Any guesses? What is 0 times n? For all 0, yeah, for all possible values of 0, it's going to be 0. Someone might say, well, 0 times infinity might be something else, but infinity is not a value, it's a metaphor. You can't multiply by infinity. So 0, I think, is the right answer. And for a long time, compiler writers were aware of this. So if your compiler was going to do a multiply, and it sees that one of the operands is a 0, that at compile time you can determine that you've got a 0 there, and if the other operand has no side effects, you don't have to generate that code. You just emit a 0 and you're done. And so the compiler runs a little faster, the code runs a little faster. This is a brilliant optimization. And for a time, all the compilers did this. Until the IEEE format came out, and IEEE said, no, this is no longer true. If n is nan, then the result must be nan, which means that you have to go ahead and evaluate this thing anyway, just on the chance that it might turn out to be a nan value, and then nan will be the result. And so all of those compilers were in error, and they all had to be revised and made slower. So people don't ordinarily write 0 times n code, but code generators and macro processors, partial evaluators do. And that code could all run faster if the number system said 0 times n is 0. There are also non-conditional idioms that could benefit from this. Modern CPUs spend a lot of energy doing pipelining in the instruction streams. And the pipelines get longer and longer, it seems, in each version of the CPUs. And the problem with that is that if you have a conditional jump, it means they can no longer be filling the instruction pipeline and everything stalls until that jump is resolved. But there's a way around that you can multiply something by something that is 0 or 1 and multiply another thing by something that is 1 or 0 and add them together. even though it seems expensive that you're doing all of these adds and multiplies, it's actually faster than waiting for the conditional jump to resolve. But that only works if we can multiply by 0 and get a 0. So I recommend that all of these forms should resolve to 0 for all values of n, just because it will allow our systems to go a little faster, and I don't feel the need to punish the wicked for trying to do something like dividing by 0. I don't have a moral stance on that. I'm more practical. So that brings me to the end. I want to thank all of you for being here and for inviting me here. This is a lovely conference. I think this is a beautiful city. I'm very glad to be here. But I also want to thank some other people who couldn't be here today because they're dead. But I owe a lot to them, and I want to thank them. So the first is Leonardo Fibonacci of Pisa. In the late 12th century, he visited Arabia and learned about the amazing things that were happening in mathematics in Arabia. He learned about the Hindu number system. He learned about what they were doing in algebra and geometry and algorithms. He took it all back to Pisa, where he wrote a book, which was published in, I think, 1202, something like that. This book was very influential. It started the idea of using decimal numbers in Europe. He taught a lot of new techniques that were adopted by the bankers, who used his discoveries in order to generate so much wealth that it funded the Renaissance. So thank you for that. I want to thank Gottfried Leibniz, a mathematician and philosopher. First he did the calculus. Thank you for that. That was great. Also, he was the first person to figure out the binary system. Well, people had played with binary, but he was the first to think of it in terms of a numerical system. And that becomes the basis of all we're doing. So thank you very much for that. I want to thank George Boole. He was a English logician who, while working in Ireland, came up with a formal system of reasoning based entirely on 0 and 1. That turns out to be a really important thing. The Boolean type is named after this man. I want to thank Claude Shannon. He took Boolean's logic and found a way to apply it to the design of digital circuits, so that this correspondence is the way we build all computers now. All of that stuff comes out of Claude Shannon, which is amazing. If that weren't enough, he also came up with a theory of information which allows for any analog signal to be represented in a digital form to any desired degree of accuracy and then back again, which enables all digital media, all networking, everything that we're doing in the world. All of that magic comes out of the discoveries of Claude Shannon, work that he did at Bell Labs. So thank you for that. Finally, I want to thank Tahuti. I couldn't find a photograph. Tahuti invented writing. He was the first human to invent writing. He discovered the rebus principle, which allowed you to use a picture of something to represent not its meaning, but its sound. By putting together the pictures of things, you can represent anything that can be spoken. He was the first person to put that together. And that helps with the unification of Upper and Lower Egypt and the society, that culture, that civilization is built on Tahuti's idea. Now, when in a religious tradition, it is sometimes said, and it is written. So when it was written, who did the writing? In Egypt, it was the scribes. The scribes took stories that were in the oral tradition that had been copied around for, thousands and thousands of years and wrote them on papyrus, and eventually they get carved on the walls of the pyramids. And as they were doing that, they incorporated Tahuti into the stories. They elevated him to be the god of writing and magic and made him an important character in these stories. So why did they do that? So obviously that was a recent invention, because there were not stories from thousands of years ago about a god of writing, because writing was a brand new thing. So they did it because they wanted to elevate their own profession, that this was something that gods did, that gods cared about. All of the other gods cared about what Tahuti wrote. And so that elevated their profession. So obviously this is something that pharaohs and managers and everybody else should care about too. So you want to keep your scribes happy. I think the other reason they did it was they wanted to thank him for giving him the best jobs in Egypt. You know, they didn't have to catch fish, they didn't have to work in the fields, they didn't have to haul the big rocks to build the pyramids. They got to sit comfortably and write on their papyrus and do the counting and the numbers and all of that stuff. It was great. So we are the children of Tahuti. You are the sons and daughters of Tahuti. You use language, you use writing to change numbers into magic. Thank you.
We now have time to take questions, so if you raise your hand, me or Bartek are going to approach you with the microphone. I can see one.
Thanks for your talk. You mentioned the DEC 64 type. Are there any reasonable other concepts to represent such numbers nowadays that you're familiar with and could explain firmly?
Sure. So IEEE tried to come up with another thing of their own, and they proposed to insert it into JavaScript. It was a 128-bit format with 10-bit fields, each field representing a number between 0 and 9999. It was very, very complicated. It was very, very slow in hardware. IBM pushed very, very hard. In fact, IBM voted against ES5 because ES5 did not include it. And the reason ES5 did not include it was that none of the JavaScript engine makers wanted it because it was going to slow them down. And they were all in this fierce competition to try to make their engines faster. And they didn't want something that was going to be making them slower, so they dropped it. I was actually in favor of it, although I wasn't happy about how complicated it was. So I came up with my own DEC 64 because I wanted to make something simpler. Another approach would be to have an unlimited precision format, like big decimals or something like that. And the advantage of those is that there are certain classes of underflow which cannot happen, because if you don't have enough bits to exactly represent something, you just add more bits. And the penalty for that is that things will obviously be slower because it's a much more complicated notation. For some problems, it doesn't matter. You know, so if I were doing astrophysics, I would definitely be wanting to use something like that. But for most of the routine processing that we want to do, I think DEC 64 will be just fine. That it is exact and correct for decimal fractions up to about 36 quadrillion. And it's unlikely that you're ever going to experience any of the underflow or other problems in the sort of routine work that we do.
Any other questions? Another one here.
When DEC 64 will be implemented in V8 engine?
You'll have to ask the V8 team. Probably never, because it is a breaking change that you can only make a change to JavaScript if you can make the claim that all existing programs will work exactly the same. And that won't be the case. There are some programs that work incorrectly now, which will now work correctly with the new number type, and that's a breaking change. We can't tolerate that. So JavaScript is what it is. I don't think we will ever repair it. We had a chance to repair it with strict mode. We could have said, when you're in strict mode, you get the new numbers, and that's it, but we didn't get the new numbers in at the same time. So I don't think JavaScript will ever be repaired. And so that's why I'm more concerned with the next language. In the next language, we have an opportunity to fix some things that JavaScript just can't fix.
Okay, we have next question. Okay, hi. I have a question about expanding the base of DEC64 because, well, right now 64-bit processors can process it in one cycle, but probably in the future we will have higher based processors. So, are you thinking about it? Will it be necessary?
I don't think it's necessary. I mean, we could very easily expand it to 128 or 256 bits, but I don't see much value in it. The thing that I would like to expand it to would be to 72 bits. I would like, but that ship sailed a long time ago. I don't think we'll ever get to do that again. I have another talk about character sets where I show the history of ASCII and how ASCII was originally going to be a 6-bit character set, but grew one more bit and became a 7th bit. But if it hadn't done that, then I think the projection of history would have been that the 18 and 32-bit architectures that were popular back then would have survived. And today we'd be looking at 72-bit architecture and maybe 144-bit architecture. And that some of the hard points that we met in our history where, you know, we had the 64-bit limitation and then the 16-bit limitation and the 20-bit limitation and so on, we would have hit those points at different times if we had stayed with the multiple of 6 architecture, which actually would have tracked closer to Moore's law, and so it wouldn't have been so painful and disruptive. But there's no way we're going to go back and fix that. So I think 64 is going to be fine for most applications. I think we're done. Thank you.
Douglas Crockford.